Okay, so all of this talk about derivatives, we're going to actually talk about second derivatives. So the first derivative is velocity, speed. The second derivative is acceleration, and that's kind of why you saw the roller coaster, is you could think of if you're on the roller coaster, the speed that you're going is the first derivative. As it speeds up or slows down, that's the second derivative. We're going to talk about the different notation and then how actually the second derivative lets us know if our function's concave up or concave down. So if I let y equal s of t is the height of a roller coaster at time t, so the position where you are on the roller coaster, then the first derivative, again, the change in the height over the change in time, or change in position over change in time, is the velocity of the roller coaster at that particular time. So then the second derivative, okay, here is the derivative of the first derivative, right? And, typically I don't write it like this, but that's what this means, or it's the derivative of velocity. You'll see a lot of times this double prime, so y double prime, which says take the derivative twice. So take the derivative, you get a function, take the derivative again, and that gives you your second derivative. All right, so this would be the acceleration. So again, just as when you drive, you accelerate, press the accelerator pedal, the gas pedal, speed up, slow down, and so this would be our acceleration. Different types of notation, once again, is if we have a particular function, how we write the derivatives in Leibniz notation. And then, as you can see, this gets a little crazy. It's just a bunch of different ways. Like I mentioned with the first derivative, I typically will use this first one, second one, or fourth one. Okay, I really like, we talked before, I like this, the change in y over the change in x, because that reminds me it's just the slope. I don't use these a lot because students get them confused thinking that you're squaring something, which you're not. I typically use these first two more with the double primes, which again just says take the derivative and then take it again. All right, so if I'm looking at a function like this, and the first derivative's negative, because we said that's the slope, so it's decreasing, and then the first derivative goes to 0, it goes flat, and then the first derivative increases. Well, that would tell me that I have a concave up function. However, sometimes it's faster, instead of going through those 3 steps, just to find the point here and see if the second derivative is positive. A lot of times students will say, it's happy, it's smiling, that's a smiley face, right? So if the second derivative is positive, then you know you have concave up. If, same thing here, first derivative increasing, we hit 0, we decrease. But if we just look at a particular point, if the second derivative is negative, then that's concave down. And that's all this is showing here in particular intervals. I can figure out if a function is concave up or concave down based on that second derivative. So this kind of overviews that. The second derivative, if it's positive, concave up. If it's negative, concave down. If you get the second derivative equal to 0, then there's no concavity. All right, so it says, are the following positive or negative? So this is getting you reading the notation. What does this notation mean? Well, f of 2 is the value of the function at 2. Well, the value of the function's the y value, so it looks like that's negative. The next one here is the first derivative at 2. The first derivative says, is that function increasing or decreasing? It looks like it's decreasing, so that's negative. And then finally, the second derivative, how do we know if it's positive or negative? We look at the concavity. Because this is concave up, then it would be positive. All right, and so that's the difference between the value of the function, the y value, the slope at that particular point, and then the concavity at that particular point. So if we want a graph, like let's say I told you just sketch the graph, what would a function look like if the first and the second derivative everywhere is positive? Well, I know that means it's increasing when the first derivative is positive. If the second derivative is positive, that means it's concave up. So that's what that function would look like. If you hear the tapping, that's Scout walking on the floor. I thought, man, that's kind of loud, huh? All right, if you don't hear it, then you think I'm a weirdo, but that's okay too. All right, so if I want you to graph the function where the second derivative everywhere is negative, so the second derivative negative means it's going to be concave down, but the first derivative is positive, means it's increasing. What would that look like? This function is increasing, but it's turning concave down. The second derivative everywhere is positive, so happy, concave up. But now the first derivative is negative, so it's decreasing. First and second derivative everywhere is negative. So the first derivative negative, decreasing. Second derivative negative, concave down, would look like this. So that's how you would sketch those graphs. Let's see an example here. It says the table gives the number of passenger cars. So cars here with the function evaluated at t, where t is in the US in a particular year, and our number of cars are in millions. It says does f prime of t and f double prime of t. So does the first derivative and the second derivative appear to be positive or negative? So during the period 1940 through 1980. So I'm just looking at these values, 1940 through 1980. Well, the first derivative looks like it's increasing. Okay, so certainly it appears to me that it's increasing. Also, if I just kind of visualize this increasing, that would be concave up. So they both would be positive. If you're not sure, plot the data. Okay, but I can kind of visualize that this data is increasing, and once again, just between those values, because if we go out further to 2000, we can see that's actually where it's going to start to turn. In a study of deaths in the US, it was found that the deaths from some aerial transmitted disease as a fraction of all deaths could be well described by this graph. So in other words, I can see here the years and then the fraction of deaths. Determine where the function is concave up and where it's concave down, and what does this concavity mean? Well, I can see the concave down and I can see the concave up. Okay, so it looks like at about 40 years, it's actually changing from concave down to concave up, so somewhere in here. So what this means is the fraction of deaths is decreasing at a slower rate. And you can kind of see that from the graph, right? That it's decreasing really fast. And then it starts to decrease a little slower because your slope's going up a little bit. And so it starts to decrease at a slower rate from 40 to 100. All right, so that's it with second derivatives. We certainly can look at the actual, how did we find the derivative, the first derivative? We use this limit formula. The only difference here is now we're actually taking the derivative again of velocity, and that's how we get acceleration. As you're going to see, we typically don't use this formula because that's using this formula twice, and that's a lot of work. We're going to very quickly get into shortcuts, which you're going to like. And that's it for, what did we just do? Yeah, to find second derivatives. See you next lecture.